Okay, so we start again, we reconvene. This take your seat. And be kindly silent. Okay, so we're going to start. We have now the lecture on Cherenkov detectors, dedicated both to detectors like supercamericante, but also to neutrino telescopes. And the lecturer is Giorgio Riccobene from the INFN Laboratory del Sud, close to Catania. And in a while, George, I will let you, I will ask you to present yourself in 1 minute. But before going to your presentation, this is an online presentation, but for good reasons. George was supposed to be here to provide the lecture directly, but right now there is this campaign of bringing down the strings of the kilometer cube detector inside the Mediterranean Sea. So he is on site at Porto Paolo di Capopassero in Sicily, ready to bring down the new strings and include the detector. So this will be the only online lectures, but I mean, this gives you also the feeling of real experimental physics. When one has to build the experiment is there, and one has to be there. Okay, Giorgio, so you can introduce yourself in, say, 1 minute.
Just 1 minute. Thank you very much. And sorry again for not being there, but there is a major sea operation running now at the KM3-NET ARCA telescope. You see there the track of the ship and the new field. I will show also in my transparencies. This is the counting room of the kilometer cube ARCA detector underwater telescope. Here we are in Porto Paolo di Capopassero. Yesterday I was still in Malta to load the ship, and this is where we are also. The counting room is close to a very nice place.
Not too bad, we can say.
So myself, I'm Giorgio Riccobene. I'm a researcher at INFN LNS, Laboratorio Nazionale del Sud in Catania. I was the former coordinator of the calibration group of KM3-NET. So I was the one who had put in place the time calibration and acoustic positioning calibration of the detector. And nowadays I'm coordinator of the astroparticle physics group at LNS. So feel free to contact me in case of doubts or further requests. You have my slides already on the Indigo page. So let's start with the presentation at this point. So my lecture is divided in 2 parts. One is a general presentation of Cherenkov radiators, Cherenkov detectors, and the second part deals mainly with underground applications of the Cherenkov technique. I will not cover indeed. I will not cover indeed very much the part connected to the photon detector, but I will mainly try to provide an overview on the technique and on the use in different experiments. Okay, so can you hear me? Perfect. Okay, can you see the screen?
Yes, we see the screen and also your mouse, I think.
Perfect. Okay, very good then. Okay, so in order not to lose too much time, let me start with a bit of history. So history of Cherenkov detection is a long one. It starts in 1936 with the discovery of Cherenkov radiation from Pavel Cherenkov, indeed, a Soviet Union scientist, that together with 2 collaborators, Tam and Frank, where theoretical physics discovered and then explained this radiation. Really, this was already somehow predicted by using standard Maxwell equations in late 19th century by Heaviside, and the first observation indeed comes from some observation by Marie and Pierre Curie in the early 20th century. However, in 1936 we have the discovery indeed. 37 the explanation, and then in 58 the Nobel Prize for this discovery. And it is actually the emission of ultraviolet and visible light by high energy particles in transparent radiators. This allows the construction that is widely used in physics, in experimental physics, of cheap particle detectors, which really contributed very much to success of high energy and also particle physics. You will see many Nobel Prizes that have been awarded using detectors built with Cherenkov technique. Actually, coming to history, the detection of the production of light by particles traveling at speed of light or more than the speed of light in the medium is a phenomenon which was already predicted and studied by Vavilov in standard mechanics. If you have a gunshot, indeed, you see there is a production of a shock, which is actually an expanding shock due to the gases. But if you look at the bullet, which travels at the speed of speed greater than the speed of light of sound in this case, you see exactly what you see then as a Cherenkov cone. In this case, is a mechanical cone, and this was described by Vavilov. Indeed, in Soviet Union, this was called Vavilov-Cherenkov effect. So we need to have a Cherenkov radiation of charged particles, and this particle has to move in the radiator at a speed larger than the speed of light in the medium. In the case of Vavilov mechanics, in the speed of sound. Okay, the first experiment that we have been carried out by Cherenkov used typically a high energy gamma ray, okay, like cobaltum or radioactive source, which actually produced a Compton scattering on a liquid radiator, okay, and then production of low energy photons, which were reflected by mirrors into a photosensitive film. Okay, what was discovered that the number of photons detected was proportional to the electron path length. The light emission was prompt, not delayed at all. The light spectrum was continuous, and the angular distribution depends on the radiator reflection index. Another property which is not very much exploited is that light is polarized with a linear polarization, but this is still something that we need to really exploit in future. But the ingredients for the Cherenkov detection are already here in this scheme. The first experiment that actually used an electron beam, 2 MeV, was carried out by Collins in 1938, and this actually produced what we actually see in every picture dealing with Cherenkov radiation. Here is a nuclear reactor, and this blue glow is indeed caused by electrons produced by neutrino interaction in water, going neutrino interaction in water. In 1951, the first observation of Cherenkov light from a proton beam happened, and in 1970, again in Soviet Union, we have the birth of rich ring imaging Cherenkov by Zrelov, which used a proton beam of 660 MeV on a thin glass radiator that actually produced a cone of Cherenkov light. So here you see the picture, the original picture. Here are the protons, and this is the Cherenkov ring. Let's go to the theory then. Okay. How Cherenkov light is produced. We have already discussed this. The real ingredient is to have a dielectric medium, a transparent dielectric medium, through which a particle passes. This particle passing into the medium releases energy and produces dipoles, okay? what is important here is that differently to the typical radiation produced in media that requires an acceleration, an accelerated particle, okay? The strange of Cherenkov light is that the particle moves at the speed which is constant, so it's not accelerated. So why this happens? Because the accelerated charge is not the particle, but the medium, okay? Dipoles that actually radiate. And what happens? If the particle moves at a speed which is lower than the speed of light, okay, in the medium, so take always into consideration the refraction index, the poles are produced symmetrically, but you have a destructive interference of the waves. While if the particle moves at the speed of the speed which is greater than the speed of light in the medium, then you have a shock waves. The dipoles are not anymore symmetrical, and you have a coherent like a light emission angle, which actually comes out from the Huygens construction of the waves, exactly as you have the sonic boom in mechanical shocks, like in planes moving at Mach more than 1. What should be noted? First of all, there is a dependence on the medium, which is also the radiator reflective index. This actually sets the threshold together with the speed of the particle, okay? So it's very important that we have a proper medium with a proper refractive index to observe Cherenkov light. And then the angle, okay? At the minimum, so just after the threshold, the Cherenkov angle is minimum, and then it increases and saturates. Following this relation, indeed, okay? So cosine of the theta Cherenkov angle is proportional to 1 over b over n, which is where n is, again, the refractive index, which is lambda dependent. Do never forget that, okay? This, as we already said, can produce different, even can allow experimental physicists to have different type of detector. And these specific theta Cherenkov will give birth to the ring imaging Cherenkov detector. Pay attention already here. I will repeat this caveat many times in the lecture, during the lecture, okay? One of the most important problems in Cherenkov detection is the chromatic error, okay? The fact that n over lambda, okay, changes in medium, so has a lambda dependence in the medium, makes one of the most complicated problems in Cherenkov detector, because of course Cherenkov threshold happens at different speed for different lambdas, okay? So if you want to have a coherent bunch of photons, you have to take into account the wavelength effect. So you can select wavelength selector, or use the radiator with a lambda which is almost constant. And in case, we will see that, for instance, in Babar or others, you have to measure the time of propagation of the photons. So you can measure this and then get rid of the n lambda effect. Another important point of this of the Cherenkov light is the fact that it's very weak. With respect to the standard energy loss in media, like the better blocks, this is an order of 1,000 less than what you have in standard energy loss. This is proportional to the structure, to the alpha of the constant, to the charge of the particle squared, to the theta Cherenkov, okay? If you integrate the number of photons over E, this is proportional to the length of the track, okay? So you have only in the end a few hundreds of photons per centimeter of track, okay? Which is, I repeat, very weak with respect to the standard energy loss and to the principle that you have already listened to during this conference. So you need optimal radiator and very sensitive photon detectors to exploit fully the Cherenkov technique, okay? The other point is that the light has a 1 over lambda dependence, as we will see, okay? And this implies that it's mainly produced at a small lambda and with a cutoff typically for radiators at ultraviolet, okay? So properties of Cherenkov light at this point are clear, because if it happens at a certain threshold in beta, it can use to tag particle, okay, and to recover the identification of the particle, and also in combination with other detectors to measure the particle momentum, okay? So you can write the threshold, the Cherenkov photons, as a function of beta, which is the simple relation that we have already found, 1 over n, okay? But you can find also in terms of gamma and in terms of momentum, depending on the particle mass. So these relations, which are always the zero relation, can be exploited to actually build your detector in order to have a selector of beta or momentum or gamma, okay? And how do you select your detector? The main trick is here. You select a radiator with a special refractive index, hopefully constant, as we said, okay? And the change, you define your radiator to have a proper selection of your particle, okay? Be careful, because changing of the detector has an effect. The radiator has an effect in the number of photons, okay? The less dense it is, the less photons you have in your producing your detector, and this affects the quality of your detector in the end, okay? The resolution of your detector, okay? This is another set of example of radiators. So as a summary of this first part of the lecture, we said we can say that Cherenkov radiator, okay, allow a fast counting of single charge particles, okay, which have an excess of velocity of beta with respect to the Cherenkov threshold. They have a prompt response and actually do not suffer a paralysis effect, okay? So because the radiator continuously emits this Cherenkov light. On the other side, on the other hand, sorry, scintillation, for instance, with respect to scintillations, the number of Cherenkov photons is much less. We said that the time is prompt, okay, which is typically not like this in typical scintillators. And Cherenkov light allows also the measurement of the particle direction, because it's very directional, okay? So now we have all the ideas to build. We have the recipe to build detectors. Now we need the ingredients to build the Cherenkov detector, okay? Cherenkov detectors, as I will show, are used in many fields of high energy physics and astrophysics. And the ingredients to build up a Cherenkov detector are mainly 3. You need a radiator, okay, which is characterized by a certain refractive index and thickness, okay? Mirrors and light collecting device, which are used to guide the Cherenkov light and to focus in case the light towards the light detector, and the light detector itself, okay? So we can use them as particle identificator, just measuring the theta, which is a function we said of the momentum. So if we measure momentum with a tracker, for instance, and with another detector and theta, we actually can have a direct information on mass and identify the different particles. We will see that, for instance, in some application that we will describe later. Okay, so another important point is the resolution. Okay, delta beta over beta or sigma beta over beta depends on how accurate, okay, we are. Our detector can measure the theta Cherenkov angle, and of course the number of photoelectrons that we collect, okay, which actually define the resolution of our detector. The other important piece of information to build up a Cherenkov detector is the fact that indeed you have to convolute the Cherenkov spectrum, which is typically has this 1 over lambda square function, okay, which comes from this formula here, with the performances of your detector. And the performances of your detector are one coarse and one more how to say, functional. The coarse dependence is the fact that your detector, typically a light detector, has a certain interval of energy, okay, in which it is sensitive. See here, for instance, typically alkali photocathodes responds as a function of the wavelength. So in this case, you have to integrate between the proper energy range. And the second one is that, of course, the quantum efficiency, for instance, of the detection is not flat, okay, but it has a dependence. This has to come into this effect. So together with the radiator properties, the photon detection efficiency is very important when you build up your detector, okay? Oh, at this point, we can build our detector. There are three main kinds of detector. One, which is the simplest, a threshold Cherenkov counter, which actually select particles with a certain beta, okay, which is greater than 1/n. Then you have simple detectors, which are the differential Cherenkov counters, which actually select particles in a range of beta, okay, between the threshold and a certain Bmax, okay, and this can be jointly used with the momentum, for instance, a measurement to identify the mass of the particle that we said before, and smarter Cherenkov detectors, which are the imaging Cherenkov detectors, okay? In this case, you measure theta c, okay, and you can identify, you measure the particle velocity, you can identify the direction and the energy. The brightest example, for instance, that we will treat is super K, okay? How a Cherenkov threshold detector works, okay? Very easy. You have a beam, okay? And you feed your beam into a gas or a different story with a liquid, okay, or solid radiator, like a thin liquid or gas, okay. In this case, the Cherenkov photons are produced inside this radiator and then guided, okay, to your photodetectors. And this is very helpful because actually this separates directly your particles, okay, your collection device from the beam, okay? In this case, you actually, what you have actually to do is to count the number of photons. Okay, in the case of the radiator, when the radiator is a gas, of course, the Cherenkov radiation happens also inside, fully inside this, the gas itself, okay? In this case, as we said, the delta B over B is a tangent square of theta C, what we said it before. And you can separate, for instance, pions from other particles. If in your beam you have pions and counts, for instance, and you select, okay, and they have an energy of 1 GeV over C, then if you choose a radiator which has a refractive index of 1.05, okay, just because of the mass of the particle and thus the momentum, only the pions emit Cherenkov light. So you can actually discriminate the passage of a pions from the passage of a count, okay? Problem is how to obtain a very well-defined refractive with and lambda. But luckily, technology helps us, and since 80s, we have the possibility to build aerogels, which are silicon-based, so actually quartz, very low dense quartz materials in which you can select the concentration of your dopant and the structure of your quartz and actually have a very well-defined refractive index. The other possibility is to use a gas, and in this case you can change temperature and pressure of the gas, okay, and change at this point your refractive index. This has been used many times, and we will see. Okay, so very simple threshold counters have been used for years in particle physics, for instance, in Na49, okay, and in this case, you change the gas pressure to change the threshold, okay? So you can change a different pressure and gas mixture, you can select your beta or your gamma, okay? and select your particle. Okay, pions, kaons, and whatever, as we have just described. Probably one of the most known examples of Cherenkov threshold detector is Bell 1, okay, in which you see here there were a collision between a plus A minus beam, and then here inside you have different, okay, detectors with different refractive index to select particles with different different particles, so with particles with different mass, mainly pions and kaons and protons, okay, at different momenta using just the N refractive index. Okay, so this is how this the module of the Cherenkov Cherenkov detector was done typically. Okay, so with the light guide to go to the PMT, and here, for instance, is a result, okay, of the separation between protons and pions in your Cherenkov counter. This was achieved up to very good energy, but remember, we have very few photons, okay? Another kind of Cherenkov detector is the Cherenkov differential Cherenkov differential Cherenkov detector. Okay, in this case, these are very much used again in lines, okay, in beam lines, okay, and in this case you can actually select with the proper setup, okay, the particles which have a very narrow range of beta, okay. So this kind of, this is again the case of radiators, and this is the case of gas, okay, in which you have in this case you are really offline using a cylindrical mirror. In the case of gas, you need a refractive, a mirror to actually put out the particles from the beam, the Cherenkov photons from the beam. And this was used, for instance, by Chamberlain and Segre at BNL to measure the antiproton. Okay. The probably most known technique in Cherenkov detector is the Rich technique. Okay, and this is widely used in high energy and nowadays astrophysics experiment, astroparticle physics experiment. And actually, you have to measure the Cherenkov angle in a proper way. Okay, in the best way possible. In this image, okay, you can see how you use, for instance, liquid or solid detectors. In this case, your particle passes through a solid thin or liquid thin Cherenkov radiator, and then Cherenkov photons are directly emitted out of this radiator in a cone, assuming that this part is very well matched with the refractive index of the radiator. The other possibility is to use gas detectors. In this case, the particle passes through the gas, and you actually need a mirror, typically a spherical mirror, to deviate, okay, the Cherenkov photons towards a wall of detectors. Okay, so this actually exploits the fact that the particle is light. The particle emits Cherenkov light in a cone around the particle itself. This was the very first time exploited at Delphi at lab by Ypsilantis and Sagino. And what is important is that you can define a separation factor, okay, as a figure of merit, which is the capacity to separate species with M1 and M2, which is actually proportional to the momentum and to the capacity of measuring your Cherenkov angle. Okay. So what in summary, I repeat this concept, what you need is that you need a window, okay, a radiator, okay, in which the particle passes with a certain direction. In this emits Cherenkov photons, and then these Cherenkov photons will be addressed, okay, guided towards a detector window. Okay. The important is that as thin is your detector, okay, and best, and the better is your capacity to not lose Cherenkov photons and to not lose the directionality, then the better performance you have in the reconstruction of the Cherenkov angle, and thus the velocity, and then the particle type. Okay, so these are very important. I repeat again, it is very important that you have a radiator with a very well controlled radiation refractive index. Okay, because the change of the refraction index as a function of lambda changes the theta c. Then either you control the photon wavelength, okay, or you have to really put them away, selecting just a number of a certain lambda. Okay, but if you select the lambda, you reduce the photon number. Okay, and then this enters in this resolution here, which scales like one of the number of photon square. Okay, square root of the number of photon. So when you choose a radiator, you have to, take into account and control very effectively the refractive index. Then for low P, it's preferable to have a large lambda to large n to lower the threshold and increase the mass separation, as you have seen from the formula. From high P, then to have a response which is how to say, as much as possible equalized at the saturation angle, then you choose an equal one, okay? And this is possible to enable with aerogels, as we have seen, okay? Of course, it is important that the optical properties of your medium, like dispersion and absorption, are very much under control. So you cannot, you need a transparent medium with very low scattering. And of course, it has to also have a radiation hardness. Okay, the first example that we have seen in particle physics it was achieved by Scintillators at Delphi at lab. Okay, in this case you have actually a very nice solution in which you had two gases. Okay, you have two different gases. You see here C6F14. Okay, this was liquid, and this is a mixture of two gases here. In this case, this was a liquid 1 centimeter target in which the radiator in which the particle passed through and produce a first Cherenkov light, and then in the gas, okay, you produce a Cherenkov second signal, and you have a second signal here in the TPC-like photon detector. Okay, and you see here, okay, the separation between pions, which are here outside, and counts, which are more massive in here inside. Okay, these are a typical signal. You see that the resolution is not fantastic. This is gas and liquid. Okay, but this was enough to achieve a separation of pions over counts, pions over protons, etc., etc. Okay, this is the liquid and the gas resolution as a function of the momentum achieved in Delphi. As you can see here, the separation is quite nice as well. A second generation of rich Cherenkov detectors for particle physics was in LHB. Okay, in this case we have the collaboration built two rich. Okay, one close to the vertex locator and one after here, just before the calorimeter. Yeah. Okay, part. One again was aerogel. Okay, and one that was okay. In rich one there was an aerogel that was removed and C4F10, and then in rich 2 CF4. Okay, this is the setup of the particle. So this is the beam. Okay, and then this is rich 1 with HPTs as photon detectors, and this is rich 2. The technique is always the same. Here, as I said, there was an aerogel that was after removed, and in the gas, okay, the production was there was a direct production in the aerogel, as you can see here. The tracks are the yellow one, and then a Cherenkov production in blue directly in the gas, and both were concentrated into the photodetector walls. Okay. And you see, of course, that now the resolution of the Cherenkov angles, of the Cherenkov rings, is much, much better, okay? And this means a better capacity of reconstructing the beat of the particle. Okay, here is how you can actually see in the matrix of element, okay, the different Cherenkov rings. And what is important is that the N, okay, the refractive index of this of the gas was very much important to have a continuous to have a proper separation, and this meant for LHB that LHCb that they had to monitor temperature and pressure constantly. Okay. And the other little ingredient was that they put CO2 to quench actually the fact that CF core scintillates. Okay, so they actually use this. Separation that they achieved is indeed very, very good. And this is one of the, most brilliant results that they had. Okay, you see here separation of muons, pions, kaons, and protons. Okay, in the aerogel first and in the gas afterwards. Okay, and this helps very much in the separation of the contribution of counts in the B0 channel, as you can see here. Okay, so this is together with the independent measurement of the momentum, then you can recover the mass of the particle, they identify the particle, and then remove the background, which was one of the major results of this technique. Okay. Another point was then to reduce, to actually tag the photons, but we will see that in Babar, and then the capability to detect the time. Okay. Last point for this first part is the use of the DIRC. Okay, which is a detector of internally refracted Cherenkov light. This is a very smart detector because you produce actually with this technique, you produce a Cherenkov light, okay, in a radiator, but then uses the fact that if the radiator has a large n, okay, typically square root of 2, 1 plus 1 means more than 1.2, actually 1.3, then you start to have total reflection, okay, indeed in this medium, if of course the medium close by is vacuum or it's close to air, okay, close to 1, then you have total refraction inside, and then you can project your Cherenkov light into your wall very far from the particle beam, okay? And this is a scheme. Of course, this has two drawback. One is timing, and one is the fact that you have ambiguities, okay? But you can use a pinhole technique, putting your PMTs very, very far from the point where the particle exits. This was used, as we said, in Babar, again, a plus E minus collider, okay? And the Cherenkov radiator was really the cylinder around the collision, okay? And in this case, you see here how big was the wall of photon detectors, about 11,000 PMTs, okay? And the separation was the number of Cherenkov tracks produced per d muons. And here you can see the resolution that they achieved, okay, to fit the Cherenkov angle, to fit the Cherenkov ring, okay. And together with, okay, and this is the separation in momentum between pions and kaons that you can see clearly here, okay. These are muons, and these are pions, and these are kaons as a function of the theta Cherenkov, okay. And then the particle identification that resulted to be very, very accurate because of the capacity to collect very much photons in this, okay. Capability to remove the ambiguities, I come here again to this reflection, okay, pattern, can be exploited with a proper tagging of the time of detection. Okay, in this case, you see that you have a lot ambiguities, but you can reduce the ambiguities tagging very much the timing. Okay, so if you have a fast trigger and a fast PMT response, you can tag and really clean the images, of course, at the cost of reducing your telescope, the resolution, because the number of photons decreases. Okay, at this point we can pass to the last argument, which is the use of Cherenkov photon detector in astroparticle physics. And one example, and then we stop for a bit, is AMS. Okay, in this case, AMS is you know, a particle detector in atmosphere, okay, in space, sorry, okay, and you have a particle, okay. In this case, it's very complex because you have a very good, very large magnet that allow, and then a tracker, TRD, and time of flight, and of course a reach. Okay, why it's used the reach? In this case, again, for PID identification. In this case, the reach actually uses a layer, okay, in which you have a radiator and then typically, as I said before, a PMT array. In this case, Cherenkov light is produced, but we will see with a special combination in the case of MS, and you actually measure again the Cherenkov angle. Of course, the spacing between these two layers sets the capacity of the separation of the Cherenkov angle, and of course, it should be optimized. Okay, this is the first attempts of using the Cherenkov technique were done in Caprice and in Cream. I will not discuss it very much in details. You find it in the slides, but you can see that you can actually with the use of Cherenkov technique start to separate the charged particle, the mass and the charge of the particles. And in AMS, as we said, we have two radiators, an aerogel and an NAF. And they can reach with this detector a separation in beta B over B, which is very good. 0.1 over theta of the charge. Okay, so this is the detector. As you can see here, the particle passes. So you can pass through an aerogel or through the ANFB window. Okay, you have the refractors here and the PMT plane. Okay, what you need is a very much pixelized multi-anode, okay, surface, okay, multi-anode PMT surface to achieve the detector granularity, which is really extreme in this case. And this allows you, together with, because the detector is very compact, to detect through the Cherenkov light, okay, to have an excellent velocity resolution and an excellent charge resolution, as you can see here, as a function of the charge, okay? And this actually ends the first part of the lecture, and we can pass to the second part, if you are...
Maybe Giorgio, we can stop for a while and see if there is any question.
Yeah.
On this first part, so mostly the basics of Cherenkov radiation and some example of detectors that are out of the astrophysics case, but I think are relevant because first of all, we are particle physicists and they also may give new ideas. There is a question.
Yeah.
My question is most out of curiosity. I'm not experienced with Cherenkov radiation. So different wavelengths of light experience different group velocities. But I was also curious, they also experience different phase velocities. So could you measure the phases of the light coming in or the relative phases to distinguish that as well? As that as a piece of extra information?
This depends on the okay. Good question. If I understand the question, is that you can measure the phase velocity or the group velocity of the light? in Cherenkov, which is, I mean, can you repeat a little bit because I was not.
Yeah, that's all right. So on top of looking where the lights are going, which is dependent upon the angle, which is dependent upon the group velocity,
Yeah.
can't you also use the phase velocity or the fact that they are all moving in with a different phase to further distinguish different wavelengths from each other, just to kind of get a little bit of extra information?
Mm-hmm. Yeah. Well, this is a good question, and really to think about that, because if you use the well, the problem there is connected to the medium itself, because you can have the effect of let me think. Not sure I can answer right now. The question is very nice indeed. Tu, 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 tu. Oh, Not sure I can answer directly. Okay, I'll have to think about that really.
Okay, thanks, Giorgio. You can get in touch anyway.
Yeah, absolutely, absolutely. This good. I mean,
There is
because
another question.
yeah,
Hi, I have a question on the theory part because I'm like this is very new to me. So is the reason why the particle is moving faster than the light in the medium, is it because the light scatters inside the material or?
no, the particle. I mean, you know that light within a medium. Okay, the light doesn't travel at the speed of light itself. No.
Yes, but I mean, the way it has been explained to me is that usually in material, it doesn't travel the speed of light because it scatters between the atoms. And that kind of takes away some of its time. I mean, I don't know.
Ah, okay. This is very, very, very basic physics then. Yeah. This is the, the the refraction of light inside the medium is yeah, it should okay. I got yeah wait I'm not sure. I mean, I'm not sure I got the question properly. So you say why the particle doesn't I mean, why the light doesn't move I mean, why light doesn't move at speed of light in the medium?
Yes.
Okay. Well, this is called yes by the fact that the question was indeed the fact that inside the medium itself the light, okay, start to find the electrical field caused by the presence of the medium itself, no, and it start to how to say well, what is the point there? You have the emission of light, and then okay, how to explain this? This is again basic physics. These are you have a chromatic. Okay, you have a chromatic effect. So the light of different wavelength doesn't travel in the medium at the same speed. So you have a speed a wavelength dependent, okay, effect. So this is not only scattering. The fact that if it were only scattering, okay, then you should have a coherent reduction of all the wavelengths, no? While the light of different wavelengths has a different speed in the medium. It's the same principle of the prism of Newton, no? Okay, so this is caused by the wavelength of the light, okay, and so different wavelength light of different wavelengths have a different behavior inside your radiator. Okay, so you have first of all a lambda dependence, okay, of your inside your radiator, and this is caused by indeed the okay, and the behavior then is that you start to have a different okay, when you okay, how to explain it in a easy way. Okay. Imagine
Maybe you postpone this reply, and for the moment we accept that in a medium light travel slower.
Yeah, no. I
And
mean,
and the ratio is what we call the refraction index.
exactly. This is the refraction. Okay. The problem is that it's the wavelength. Okay. I mean, if it were just scattering inside, okay, then you would add a coherent, okay, change for every wavelength. Okay. So there is a lambda. What I mean is that there is a lambda dependence. You have to take into account. I mean, it goes back to the question of the group velocity and the phase velocity. Okay, when light comes into a medium, okay, from I mean, imagine you have the radiator inside, okay, in the before vacuum and then radiator, then you have a change, okay, of the wavelength. Sorry, inside. So this changes. How to say? How to explain it? When you come into the medium, okay, then you change somehow the wavelength. No, it's okay. I will tell you later. I have to find the right words to explain. But anyhow, this effect is a wavelength dependence effect. It is not easily explainable as a simple scattering, because that would be a little bit different, and it deals mainly with the interaction of the field of the particle with the field of the atoms in the medium. Okay, I will keep in touch. I will give you some hints on this point. Now I'm not. It's not easy to explain.
Okay.
Okay.
Any other question?
Yes. Can we go?
Sorry, in the page 18. Sorry, can you hear me? In the page 18. Sorry.
I cannot hear you very well. Sorry.
In the page 18.
18?
Yeah.
Okay. Hold on. Oh, sorry. Hold on a second. Yes. Yeah. Oh, sorry. I have to change the screen again. This was 18, right?
Yeah. Why the PMT is perpendicular to the beam?
Why?
The PMT is perpendicular to the beam.
Can you repeat the question, because it's very difficult to hear.
The question is why the PMT in this setup is
Perpendicular. Because okay, sorry. I explain it here. Okay. Imagine this first experiment. Okay, if you put your detectors in front of the beam, then the beam will actually start to exploit to spoil your detector. Okay, so if you have an intense beam, you want that the Cherenkov photons and your detector are out of the beam. Okay, because you don't want to put your detector in front of the beam because of the fact that the detector itself can be spoiled. Okay, if you put photosensors here in the beam or close to the beam, then the photosensor will be hit by many particles.
So it will be damaged, and also the charged particle in the glass of the PMT may produce other charges.
Exactly.
So this is a mess. So you take the PMT away from the straight line of the beam.
So you actually, these are beam monitors, indeed, many very well used as beam monitors, but the fact that you are dealing with the Cherenkov photons, so with light photons, allows you to use mirrors and then to take away the radiation that you want to measure out of the beam. So you have a clean environment here, okay, for the measurement. And as Marco was mentioning, you have here as well. You may have Cherenkov light in the glass of the wind of the photon itself. Your beam can damage your detector, so you want Cherenkov photons to be out of the beam. And this is a fantastic method to achieve it.
Okay. Other questions? Okay, so I think you can go on with the second part.
Yeah. Okie doke. Okay, can you see the screen?
Yes, you can go on. You have about 50 minutes.
50.
50.
Okay, 50 minutes is okay. Okay, so you have the second part is more mainly dedicated to underground and astroparticle physics. Okay, so one example that you have already seen in Barbara's lecture probably is the muon beta xenon, because this is you are there. Marco is the one of the most important scientists in the xenon collaboration. So in this case, the muon Vito is made of liquid, okay, of water, okay, which actually surround the main detector, which is a TPC, okay, and you put water and you put a Vito, okay, and you put a layer of PMTs, a wall of PMTs that actually can tag, okay, events which pass inside the Vito before entering in the real detector. Okay, so you can actually, with this method, you have seen it before, tag a fiducial volume, okay, which of your detector with tagging particles before that enter in the detector before the real detector for that matter. So in this case, again, the ingredients are a radiator, okay, which is water outside the xenon TPC, and a wall of photomultiplier tubes that actually surrounds the main detector. This is a typical use of a Vito, okay, for particles, and another clear example, and one of the first example in dark matter measurement, okay, in dark matter detectors. One of the I mean, probably the most famous rich detector underground, okay, in this case, the previous one was not, was a parenthesis, was not a rich, but indeed counting. And one of the most important example of rich underground, okay, is Kamiokande. Okay, in this case, we had the detector was built in early 60s as a proton decay experiment, and D means nucleon decay experiment, okay? And it was designed mainly for this, with an enormous mass of water deep underground, and together with proton decay started to measure neutrinos. And of course, this became a very important detector because it discovered actually the neutrinos from supernova 1987A, okay, and got a Nobel Prize. At the same time, another Cherenkov detector was built in Irvine, Michigan, BNL collaboration in the US, which was a IMB. Okay, so you see here actually a report historically detection of the supernova with the number of neutrinos as a function of time. So why you build and how you build a rich detector underground and what you need for it. You need a large mass, okay? Why a large mass? Because you want to detect neutrinos or nucleon decay experiments. So you need an enormous mass, more than a large mass in this case. This acts as a large active volume, okay? And you have to reduce the background. How do you reduce the background? First of all, you go deep underground to reduce the cosmic background, cosmic muon background. You use ultra pure water, okay? with water purification system. And to increase the capacity to reconstruct your events, you use a very large area PMTs. You see here the enormous PMTs in this case. Okay. Super Kamiokande was the step after Kamiokande with something, just to give you the dimension, 50 kilotons of purified water. It was built 1 kilometer underground, and he used 1,000 large PMTs. Okay, it was built in Japan, and the capacity of detection of events is shown in the next slides. Okay, it's very famous because it's of course detected the atmospheric neutrino oscillation. Okay, what is the need and how is used Super Kamiokande? Super Kamiokande is used for reconstruct the momentum, the vertex, and the identification of the particle, and this is all made using water Cherenkov. This is a fantastic detector from this point of view, okay? Because the vertex is and the direction is found. The direction is poor a bit, but the timing is obtained by the timing of the PMTs at the ring edge, because this is, as we said, this is the perfect alignment with the saturated angle. Okay. The momentum is recovered by the amount of light inside the ring, and the particle in D, as we will see, is the sharpness is obtained by the sharpness of the Cherenkov ring, okay, and the opening angle of the ring itself. Okay, these are some figure of merit of the detector. So take into account, don't forget that the path of Super Kamiokande, the typical path of tracks in Super Kamiokande is 50 meters, okay, maximum. Okay, typically you have muons, okay, which actually lose about 2 MeV per centimeter, so you have a longer track in case of muons, and short tracks in the case of electrons, which produces shower and then produces more photons in this case, but the track is much fainter. So actually, based on what I said, that the fact that muons are produce longer tracks, okay, and are almost naked, so no particle around, while the electrons produce showers and have short tracks. With Super Kamiokande, actually, with an enormous pixel-led the wall of detectors, you can actually, just from the shape, okay, of the ring that you collect, in one case is very sharp, in the other case, due to the formation of showers around the electrode, is fuzzier, you can detect electrons and muons. You see here the ring, the difference of the ring, okay? So you can actually, from the sharpness, define the PID, and the timing can give you the particle direction, okay, because of the Cherenkov angle. So from the time you recover the particle detector, and from the number of its PMTs, okay, you can recover the energy of the particle itself. Okay, what is nice to see here is that it is better to count. What Kamiokande found is that it is better to count the number of its PMTs more than the reconstruct the charge of PMTs to reconstruct the energy. This is a better proxy. Okay, as you can see with this technique and with such a large detector, do not forget the speed of light in water is 23 centimeters. Okay, you have an electron, okay, like particles which produce okay, this is the timing, okay, of okay, with the timing, I'm sorry, with the timing accuracy, so you need a very good time accuracy in your event reconstruction, you can achieve a vertex resolution which is about 10 centimeters, either for E-like, you see here, which is spreader, the resolution, and for mu-like events, which is sharper, as we described before. Okay. and the energy reconstruction is very very good as well and increases with, of course, energy. Here you see the typical low energy events with very small, number of hits, 6 hits per MeV, with a vertex reconstruction, which is in the other side very, very large, because you get less Cherenkov photons. The larger is the energy, the better is the resolution, In case, just to understand the technique, in case your event is fully contained into the detector, you have a ring, in this case it's an energy electron. When the event is partially contained, you start to see not a ring, but you see this happens, but you see how to say, a filled area, because the event happens very close to the wall of the detector. So you start to have a Cherenkov light formation, and then the muon escapes, and this is the maximum. This is the ring defines when the muons start to approach the saturation. And these, of course, are through-going and particles that goes out. The next step for Super Kamiokande is the completion with hyper-K, which will happen in 2027. In this case, the detector will scale by a factor 10 almost, from the use of 11,000 photomultipliers. So they will reach 40,000 photomultipliers and lower the threshold to 6.5 MeVs. This is under construction, and you will hear really a lot. And as you can see, they put in their material 2 Nobel Prizes here, hoping for a third one. Now let's try to change subject completely, and we start to describe Cherenkov detectors for detection of ultra-energy particles. In this case, we can detect ultra-energy particles as cosmic rays, photons, cosmic photons, or cosmic neutrinos, as we will see. Let's start from cosmic rays and gamma rays. In this case, Cherenkov radiation is used in 2 different, actually 3 with the radio, which we'll cover later on, in 3 different ways. The first easier technique, it's on the right. You have a very high energy photon, in the atmosphere, which start to interact and produce a shower of particles, alla Bethe Heitler, so the typical toy. So you exploit the fact is that the atmosphere is a real calorimeter. These showers start to produce 2 kinds of light. One is isotropic fluorescence, and the other one is a very collimated light produced by particles moving at a speed which is larger than the speed of light in the medium, because the refractory index of atmosphere is a little bit more than 1. So this is direct Cherenkov light that comes from high energy photons, and this is the so-called air Cherenkov technique. And this is very much used, as we will see, in gamma ray, ultra energy gamma ray or very high energy gamma ray detectors. The other technique is the use of Cherenkov counters, Cherenkov detectors, to actually measure the passage of muons, or typically muons, or charged particles on ground, which are being produced by the development of a shower in the atmosphere. So in this case, the shower develops completely, and the muons produced by cosmic rays, are or electrons are measured with the Cherenkov tank with particle detectors, for instance, Cherenkov tank at the surface. So in this case, this is exactly, I mean, it's very similar to the previous one. The point that you actually limit in the Cherenkov atmospheric Cherenkov detector is the fact that you have a very limited field of view. In this case, you see This is just 1 degree, which actually means a few hundred meters from the source. And the light is very directional. So in this case, you have a very limited field of view of your instrument, and you have actually to move your instrument in the direction of the source you're looking for. Okay, so for atmospheric Cherenkov detectors, sorry, I'm moving very fast. Okay, you have to move the dish of your detector in the direction of the source that you are, or in the direction of the source in the sky that you are looking for. Okay, and of course you are limited by the fact that you look for moonless skies. Okay, night skies, and you need, as we will see, the capability of discriminating between gammas and hadrons. Okay, in the case of surface detector, these are, how to say, auto-consistent detectors, as we will see. And in this case, you will have a very large field of view. Okay, ideally 4 pi to pi. Okay, and very high duty cycle. Okay, so in this case, either you use, in another way to show it, either you use a Cherenkov, okay, detector, and in this case you have to point to the direction of the particle. In this case, if you want to measure the fluorescence, it can be out. If you want to measure the Cherenkov, it has to be in the direction of the axis of the shower. Or you just put your detectors on the ground, and these detectors can be Cherenkov detectors, and you wait, okay, for the Cherenkov, for the shower front of charged particle that produce your signal into the detector. This is the technique used by Lasso, Pieroget, Oak, and Zwigo. Okay, let's start with a bit of history with the Oak. Okay, in this case, Oak is a high altitude water Cherenkov, in which you have Cherenkov tanks like this, okay, filled with pure water. Okay, and in each tank you put photomultiplier tubes. When a particle of the shower passes through the water of your detector, it produces Cherenkov light, which is in turn detected by your PMTs. And at this point, you have a trigger. Okay. How do you measure the energy and the direction of the axis? Just measuring again the number of heat, okay, tanks, okay, and the number of photons detected in each tank, okay, and then you can reconstruct the shower axis from the timing and position of the heat tank, okay. So this is actually the technique used by Oak and by many others detectors, as we will see. The second point is that you need to have a gamma hadron separation, which is very important in this kind of detectors. And this is actually standard physics, because when your shower develops, the fluctuation, so the shower-to-shower fluctuation for gamma showers are very small, and the shower is very much confined within a molar radius. Okay, so you actually have your Cherenkov tanks heat very confined, and all the energy is deposited in very small number of Cherenkov tanks. While for the showers, for the big showers produced by larger showers produced by hadrons, then you have the multi-cascade electromagnetic cascade, which produces a separate spot. So you see here the difference between a gamma shower here and a hadron shower at different energy with different spots, and also here. Okay, so in this case, Cherenkov detectors are used to actually as independent single detectors, okay, that then form the big detector. Okay, another example is Lasso. Okay, and in this case, Lasso has a little bit smarter technique in which your water Cherenkov detector array is made by 3600 shells with a volume which is enormous, 19 square meters. Okay, shells have different dimension and displacement, but it's actually, here you see there is a curtain, okay, in which which actually separates for PMTs in this case. It has a 10 by 10 dimension here, and you see here the difference between a muon, that it's actually naked one, which produces a clear Cherenkov ring, or cascades produced by electrons, okay, which actually can count more. And of course, gamma and electrons are very similar. Okay, so you actually again can exploit the fact that the ring technique actually to separate this. Okay, and of course the number of muons gives you the charge of the cosmic ray, and in case you can separate gammas, okay, gamma hadron separation exactly with the same technique used in OC. Okay, another technique that LASO exploits is the fact that they have also Cherenkov fluorescence detector. In this case, these detectors are more fluorescent because they do not typically follow the source, but they are for pi. But this can allow the detector to have a combined technique that between surface detector and fluorescence detector. This technique was first exploited by Pierre Auger detector. Okay, in this case, as in the case of OC, okay, the detector uses big Cherenkov tanks, okay, with PMTs, and when a particle, muon, passes in through water, the interior is reflective, it starts to produce Cherenkov light, which is in turn is detected by 3 9-inch PMT tubes. Okay, in this case, each tank of the detector is an independent detector that performs a local trigger and sends the information of the passage of a particle to a central station. Okay, this is the displacement of Cherenkov tanks. This is Auger as an area which is comparable to the size of the city of Paris, with, as I said, 1,600 Cherenkov tanks distributed over 1.2 square kilometers, so enormous. And you can see that the passage of a particle produces, in the production of a shower, produces in turn a pattern of heat Cherenkov tanks. Okay, now what to do when you have the number of Cherenkov tanks heat, okay, as a function of range of from the shower axis? You can reconstruct efficiently the cosmic ray direction from the time pattern and the heat, but also the energy. Okay, because there is a famous Illas relation that tells you that if you have a sparse detector, okay, with a grating of more than 100 meters, then the density, okay, of particles at a certain distance from the shower axis is proportional to the energy of the particle, of the incident particle. In the case of Auger, this is about 1,000 meters. So it's enough that you count the number of particles as the number of heat tanks as a function of the core distance, and you select the figure of merit at 1,000 meters from the core distance, and then you have exactly you have the energy of the shower. Okay. Now in the core, of course, the triggers will be more fuzzy, but for more distant showers, for more distant tanks from the showers, you will see that there are the particle can be counted one by one from the trigger, and the density, as I said, of the heat at a certain distance from the core shower gives you the measurement of the energy of the particle. With the similar technique, the Zwigo collaboration is aiming at build a detector in the south hemisphere of the Earth to complement the OC and in the northern hemisphere. and it will be again. I mean, I just put it here for your knowledge because it will be used in. I mean, it's a growing collaboration. Step back and discuss about Cherenkov photons. Okay, detection. So air Cherenkov technique. So we said that the other complementary technique another technique ideal to measure high energy photons in the atmosphere is the air Cherenkov. Okay, the air Cherenkov exploits the fact that the refractory index of air is not 1, but it's a little bit larger than 1. Okay, and then when a shower is produced, okay, a charged particle are produced in turn, and they produce, okay, Cherenkov photons at an angle of 1.3 degrees. Okay, so this Cherenkov light can be detected by a detector which actually has a mirror and a camera of PMTs, okay, in the focal plane of the mirror. In this case, we exploit the fact that the light is directional, okay? So we can actually point the source with our telescope, okay? And observe all the showers, the gamma showers produced in the direction of our source. The number of photons produced is very small. We have seen already before in the first part of the lecture, it's of the order of few tens photons per square meter. But the good characteristic is that it is a very short burst of photons, so very good to make a good trigger. And of course, this happens in the visible, ultraviolet and visible range, as we said, thanks to the fact that given the characteristic of the refractory index of air. Okay, so the point is that in order to have a better resolution, we have to build large area mirrors, so alla magic. So larger mirrors means more photons, means lower threshold in energy. Okay. On the other hand, if we want to have a very good photon direction, okay, we need good timing to reduce the background, we said, to have a proper direction, and optimal granularity, okay, to actually reconstruct properly the Cherenkov signal, and also a good granularity and good timing allows you to, as we will see later, to achieve optimal hadron gamma separation. Okay, so together with the characteristic of the detector, so maximum number of pixels in the camera, perfect mirroring. It is very important in this site. You will see also in the Cherenkov, underwater Cherenkov, to select the site which has optimal conditions. That means air quality, proper altitude to exploit the fact that the formation of the shower happens at typically 10 kilometers from the sea level, and we need a very low optical background. That's why we don't build the Cherenkov telescope in cities, but in mountains far there. So how looks like a Cherenkov shower, okay, in a telescope with this strange drop, okay, image, okay, this which takes into account the elongation of the shower, okay, from its formation to the maximum to the disappearance of the shower, okay, and this is reflected into the mirror and then into the focal plane of your camera. So typical radius of Cherenkov, okay, of Cherenkov light produced by the shower is about 200 meters, okay, because as I said, the maximum happens typically at about 100 kilometers from the sea level, and the illuminated area on ground is very, very large. But as you can see, the light arrives at the photo camera within a few nanoseconds. So it's a very short burst. Okay, and these are the threshold of the Cherenkov emission. Why they are important? Because the lower is the threshold, the capability to reconstruct your threshold, the better is your detector. So more you collect light, the more light you collect, so big mirrors are the magic, the lower is the threshold you can achieve. Okay, of course, this is the minimum that you can get. Okay, so as a summary, showers develop in the atmosphere. The charged relativistic particle emit Cherenkov radiation. Photons arrive at the mirror of your detector, which is at the surface, get reflected, okay, and then you see on the camera, okay, the projection of your shower, okay? Given the fact that hadrons produce multiple shower, okay, multiple electromagnetic showers during the propagation, a hadron, okay, shower is observed as a fuzzy, okay, with a fuzzy pattern on your camera, while a shower, okay, a gamma shower has a very nice ring and if it is very central, or a very nice elongation. Of course, what you exploit to reconstruct your shower is a image analysis, okay, with some figure of merit, which is the distance from the core, the elongation, and the length, okay, the width. Okay, this is very important because, of course, cosmics are much more than gammas from the source. Okay, so they dominate the pattern, so you have to clean them out. So analysis of your pattern in your camera, okay, and different quality cuts allow you to separate the gamma, okay, very clear images, okay, from the fuzzy hadron images, okay? Oh, Cherenkov has an enormous contribution due to the backgrounds, as we said, okay, and the backgrounds and the limiting factors are several, because you're working now with another old medium, okay? So you have to consider the fact that the atmosphere is a natural medium, and then you have molecular absorption bands. You have Rayleigh scattering on molecules. You have Mie scattering at large angles due to Mie effect of aerosol. You have the clouds, you have the muons, etc., etc. And last but not least, you have a geomagnetic field impact. So you have a deviation from the original axis due to the fact that the geomagnetic field bends the charged particles in your shower. Okay, so all sum, you have to really take it under control all these effects to really reconstruct a proper image like this one from a source in an air Cherenkov. So this is the drawback of working with a natural medium, that on the other side gives you a free and a cheap medium as a calorimeter. So it's a costless calorimeter. You pay this in terms of taking under control the quality of your radiator. Last few slides on this argument is the fact that contrary to the complementary, not contrary, complementary to the technique in which you enlarge your dishes to lower the threshold, which is the route followed by magic in this field, you can choose another route, which is to have detectors which are smaller, so higher threshold, but many of them. Okay, this is the case of S. Okay, Hess, which was built in Namibia, Magic was in La Palma. In this case, the collaboration preferred to have more small telescope, but to perform a stereo image reconstruction. In this case, actually, you sum up the images of the 4 telescopes, and instead of having just one parameter, okay, with just one image, okay, to cope with, and one distance. You have several images all together, okay? I remember that Cherenkov photons arrive almost all together at the ground, and in this case, you have a stereoscopic image, which allows you a very good resolution with of SoUP degree in reconstructing the position of your source, the direction of your source. Okay. In this case, the energy resolution is also good, but the shower threshold is very high. So this Cherenkov technique is used by many detectors, Veritas in the US, EGRA was the pioneer in Canary, and then Magic NS and Kangaroo in Australia. And they actually are the responsible of the detection of gamma rays detected by energy sources. So they are really excellent detectors for energy gamma rays the detection. And the future of gamma of Cherenkov detector on ground of Cherenkov is CTA, okay, which have actually decided to use a combination of medium, large, and small size telescope. Okay, medium size will be distributed in the two sides of the detector, north and south, that are foreseen in Canaria and in Chile at ESO, while larger telescope will be used in the northern hemisphere and small telescope will be used in the southern array in ESO. Okay, with different energy threshold for large, which is only 150 GB, and small, which is 5 dB, okay, respectively. But with this medium-sized telescope, okay, which can reach, which actually bridge the two techniques, okay. And so with respect to Veritas, Hawk, etc., you will see that CPA plans to have really sensitivity to gamma rays and angular resolution, which is excellent, okay. But we will see. Last but not least, and why I'm here after many nights, is the neutrino telescope Cherenkov technique. Okay, in this case, we build underwater, we build a telescope underwater, okay, to have an enormous mass of target medium a la Super K, so we use water as a target and also as a Cherenkov radiator. The idea is to build a detector capable to, as we will see, detect neutrinos from 10 to the 9, so from 1 GB to many electron volts, okay, more than 10 to 15 and more, okay. The quest for neutrino telescope is very active. We have Chem3Net in the Mediterranean, where we are in this moment, IceCube in the Antarctica, but we have also a Baikal detector in Baikal Lake, okay, at 1,000-meter depth, and a new project, which is Speed1, being developed at Victoria Island, in Victoria, in Canada. Okay. The father of the Mediterranean detector, Antares, was built in Toulon and now is dismantled. Okay, how a neutrino telescope works? A neutrino telescope works, as I said, detecting the Cherenkov light produced by particles, charged particles produced by a neutrino deep in elastic scattering, either in water or close to the ground, close to the detector, and then propagating in the transparent medium. Okay. A neutrino telescope can detect charged current, okay, interaction, okay, like with the production of muons or electrons, or charged current and neutral current. In the case of a charged current and which follows a muon production, so if it is a muon neutrino, you have thanks to the propagation of a muon to the low radiating to the fact that the muon is very penetrating and has a radiation threshold which is very high, you have a bare muon actually with the production of a really track, okay, which heats which produces Cherenkov light in turn and produces heats on your PMTs, and this results in a kilometer-long track, okay. While if you have a charged current of that produces an electron or a neutral current, so you exploit the vertex, okay, then you have immediately a cascade of particles, which in a sparse detector, okay, produces like a bulb of light which expands, okay. That's why we typically call the event by topology tracks, which correspond to typically to muon, or cascades, which could be neutral current events, vertex, okay, or charged current electrons, or taus, okay, which are really cascades, okay. There is also the possibility to have a double bang in the case the neutrino is a tau neutrino, and then you have the interaction, then the decay of the neutrino. In this case, you have a double bang, okay, produced. The reconstruction, of the wavefront happens because you have really with timing in this case, okay? So time and position of the events is the crucial point. We do not reconstruct rings, but actually we reconstruct the Cherenkov wavefront. So when a particle passes close to the detector, then actually you have to minimize, okay, the minimum distance from the PMT, okay, is the minimum time the PMT is achieved when the track passes close into the PMT. So if it is a muon, you see that this will be hit as time 0, while the light produced before by the track, okay, happens at different timing with a simple algorithm that actually tells you which is the time of detection, okay, and the distance from the detector. You can reconstruct easily your wavefront. It is important that if you have different tracks, you will see in a minute here, if you have showers produced at a certain point in the track, showers behave like start to emit, okay, the light here. So they will be seen later than the main particle. And take in mind this, because this is a nice plot that you will see later on. Okay, so these are timing detectors indeed. Okay, so the main indetermination is in the size of the PMT. Okay, and you need a very important timing, a very optimal timing to tag to reconstruct the Cherenkov front through a simple equation like this. Okay, so this is what you actually see in a detector. Extract the tract from the Cherenkov light that hits your PMTs. Okay, so a neutrino travels, it's produced by a source, produces a muon or a charged particles shower, and produced by Cherenkov light produced by the array telescope. Okay, the two big projects have been so far IceCube in the Antarctica and Antares nowadays dismantled in Toulon. Okay, and why they have become the edges very important in recent years, because IceCube started to detect the first neutrinos from outside the solar system. So the first cosmic neutrinos at enormous energy, TeV or more, and even PeV. IceCube is built in the Antarctica ice with more than 5,000 photomultiplier tubes deployed in deep ice, 1 kilometer from deep from the ice cap. Okay, the detector is here. It has the large area PMT. Okay, with the electronics, and the signals are brought to surface to form the trigger and the event. When a neutrino passes, okay, it starts to illuminate the detector, okay, forming this pattern, okay? In this case, the light is, the time of the light is given from the color, and the intensity of the light is given by the size of the event, okay? So, IceCube identified many, starts to identify PV neutrinos with just counting the number of hit PMT. I told you, this becomes the energy estimator of the detector, and the direction is reconstructed by the sequence of events that are sequence of PMT that are eliminated. As I said, IceCube detected for the very first time, and now with an enormous accuracy, the flux of energy neutrino above TeV, which comes definitely from outside our solar system, and which are probably the plateau of extragalactic high energy events and singular neutrino events. And IceCube was also capable to identify for the very first time two sources. Okay, this is a claim because it's still diciamo, the number of events statistics is below 5 sigma, but we start to have evidence of neutrino signals from two sources, or hints, not evidence, which are active galactic nuclei, and that produces most probably neutrinos in their core vicinity, and they start to be, and IceCube start to observe excess of neutrinos from these sources. So this is the very first time that we have evidence of hadronic sources, hints for hadronic sources in the universe. In parallel, together with IceCube, we are building KM3net in Capo Passero. Again, in the concept is very similar. We deploy an array of PMTs underwater at 1 kilometer, 3 kilometer depth in this case, with strings which are 750 meter high, okay, and they're filled with more than 200,000 photomultiplier tubes, grouped in 31 in these modules, okay, which act as a fly's eye, independent fly's eye. Actually, KM3net is not only ARCA, okay, which is under construction here at Capo Passero, but also a smaller detector, a factor 4 smaller, built in Toulon in the place of Antares, okay, which is dedicated to the search of oscillations in the abysses. It's a kind of super Kamiokande, larger but less granular in the abysses. Okay, I will concentrate on ARCA. Okay, the detector, as I said, is formed as a fly's eye detector, with 31 small PMTs, contrary to IceCube, okay, which are one big PMT, and it looks in every direction. Okay, PMTs are grouped together in a line, which is folded into this unit, which is about 2 meters, which is then deployed, put underwater, connected to a network of cables that brings the power underwater and brings the signals through optical fibers on shore, then released, and then you form. So this is released, and you actually end up with a line underwater. Okay. In this moment, we are in a major sea operation, which will extend the detector from the actual 28 line to something like, which is in the range of 35, 40 units, okay? And this will make the KM3net the largest underwater detector in worldwide, okay, and complementary to IceCube. Why it is important and complementary to IceCube? Because to filter out the cosmic rays coming from above, okay, so from the surface of the detector, the detector, the neutrino detector is optimized to look in the horizon or down, okay? Chem3net can look also upward, but the optimal detection is upward, okay? So being ice cube and Chem3net in opposite hemisphere of the Earth, they can look at different portion of the sky, and Chem3net can look very much better than ice cube to the center of the galaxy. Okay. Figure of merit: the better is your capacity to track, okay, to reconstruct the direction of the event, the lower is your background, okay, and the better is your capability to reconstruct the source, of course. So what is important for such a detector is the heat time, okay, of the event to reconstruct optimally the direction of the track. And also, if you have an excellent timing, you can reconstruct very well also the showers tracking, which is more difficult, okay? Not as good as the tracks, as you can see here. Here's the resolution of the track angle, of the reconstructed angle as a function of energy, okay? But you can achieve excellent tracking resolution if you have a very good timing, okay? So if you synchronize your detector optimally, you can achieve, so with the detector, with each detector synchronized with less than 1 nanosecond accuracy, you can reconstruct better the track in the angle of the drawbacks. Yeah, we're finishing. Yeah.
Time is over, so I think we can go
We
on.
can conclude. Okay, we can conclude that we have, of course, we have, of course, to deal with the natural medium. Okay, so we have to consider scattering and absorption, and in this case, the scattering and absorption is very much better in water. So Chem3net ends up having a better resolution with respect to ice cube. Okay. On the contrary, I'm over. We have the background light due to potassium-40 and small creatures down there. The good news is that we have an optimal positioning system because contrary to ice cube, strings moves. I skip a little bit, but I want to show you the fact that with a detector which is not yet at the size of ice cube, we have detected last year the highest energy neutrino event ever recorded so far, even by ice cube. An event which is more than 10, which is about or more 10 PV and illuminates all the shower. So just to see how it looks like, you see here this neutrino event, neutrino-induced event, which produces so much light. And what other important information is that, as I said before, we can reconstruct singular tracks, okay, produced by the neutrino event, in its propagation. Last but not least, please, you will find in the slides another possibility to produce Cherenkov light. The Cherenkov signal is not as Cherenkov light, but Cherenkov radio radiation. In this case, either the geomagnetic effect or the Ascarian effect can produce in a core of a shower a signal which is coherent. Due to the dimension of the shower thickness, this cannot be light, but the coherence is reached at radio pulses. Radio as the refraction index of radio is of atmosphere for radio waves is very good. So is optimal. Sorry, very good. Is optimal. So we can detect the Cherenkov radio pulse, and this is what Anita start to do with in the Antarctica, and nowadays many projects do that. Here you have a summary. Last but not least, nowadays Cherenkov is used also in medicine, okay, in medical physics. You see here an image of Cherenkov radiation inside the bulb of a patient, and is used as real-time imaging in in medical physics, just to orientate, just to see the beam, the effect of the beam. You see here in the mammals treatment or in eye treatment. Okay, so after 90 years of from discovery, Cherenkov radiation detectors are in very good shape, are simple, cheap, and can be used for build up enormous detectors nowadays, but also in very delicate application as in medicine. And one point is that polarization is still not exploited. So I'm done. Sorry for I'm very tired in these days, so I beg your pardon for exceeding the time. But I hope I gave you a wide view of how Cherenkov detectors are used in particle and astroparticle physics. Sorry.
So we thank you, Giorgio.
Thank you very much. Oh, can you hear me?
Let's see if there are questions. Yes?
Just a little curiosity, I want to know if the presence of impurities in the water or in the medium you are using influences the detector in some shape or form,
Absolutely.
like it or the angle of the cone or something like that.
This is a very important point, and the number of impurities in water affects the scattering of Cherenkov light. Although this is just to show you, okay. Sorry, this is what we are just gathering now in online. Okay, the effect of impurities in water is very important. I go back to my transparencies for a while, and this produces okay, scattering. Okay, I give you here the example of ice cube. Okay, in ice cube there is, for instance, a layer. This is the depth as a function of wavelength, the effect of the scattering. Okay, you see here that there is the dust layer which is very high in ice cube. Okay, which limits very much the propagation of photons. In ice cube, for instance, this dust, okay, scatters and absorbs photons, and this part of the detector is actually non-active and can influence the rest of the detector. The same is valid in water. In water, luckily, we have selected a site which is here in offshore Sicily and between Sicily and Greece, which is very deep, in which the number of contaminants is very small. I show it here. Yeah, you see here. Okay, this is the number of organic particles and then scattering particles as a function of depth. And you see that this site where ARCA is built is such that below 2,000, 5,000 meters, okay, the number of scatterers is very small. Anyway, so this influences the scattering. Anyway, the light scatters, the water scatters itself as a Rayleigh, okay, so with the large angles, but the scattering is the scattering coefficient is very small. So you have anyway a scattering from the water molecules a la Rayleigh, but it's very small, of the same order of what you had in supercamiongrande. While the concentration of contaminants should be taken into account, and you have to select a very clear site. I hope I answered the question.
Yeah. Other questions? Yes?
Thank you for the presentation. I was wondering how you keep track of your detector response over such a large volume of a dynamic system like water.
This is indeed very complicated. You have to actually what you have to take into consideration for the response of the detector is to monitor constantly the response of each single photon, of each single photon detector. This is made using potassium-40 as a natural calibration source. So actually, you have potassium-40 dissolved in natural waters, okay? the decay of potassium 40 produces electrons through this chain, which in turn produce Cherenkov light. Okay, so Cherenkov light, typically at a rate of a few 10 kilohertz, is detected by pairs of PMTs. Okay, so if your detection rate is constant for all PMTs, for all pairs of PMTs in a DOM, and then for all the PMTs of your detector, then you are working in stable conditions. Otherwise, and you start to observe it because of loss of a little bit of aging and the loss of from the aging on one side, and in the other side, the fact that the photomultipliers start to be covered by a little layer of dust after some operation. So what happens is that the PMTs on your top layers, on the top part of your detector, start to lose some efficiency. Okay, and then you have to make a dynamic Monte Carlo simulation that takes into account the loss of efficiency of your top PMTs. Okay, so this is something that you have to take into account. With respect to the timing, so this is efficiency and gain, no? Okay, of your PMTs. On the timing is constantly monitored. As I said, using the coincidence of potassium 40 at the level of a single DOM, and using other sources, which are a laser beacon and an LED beacon, which are installed in the bottom of the detector and on each PMT. Using these devices, you can actually continuously measure the timing efficiency of your detector. These are indirect measurement. There is also a direct measurement of the timing of your detector, which is made, I hope you can see that, online, exploiting the characteristic of this new paradigm for time synchronization, which is White Rabbit. The Chem3net exploits completely White Rabbit, which is a paradigm in which you have a switch, actually an Ethernet switch, that through a network of optical fibers communicate with a slave underwater. The communication can be done in cascade. You see here a complicated architecture, but imagine you have a master that talks to a slave. In this case, the slave is this little board, which is called CLB, which is installed on each photon detector, okay, PMT. And then you make a round trip time measurement, okay? So you send a signal, and then these answers on and sends back your signal to the master, okay? In this round trip time measurement, okay, which happens through a network of optical fibers, but imagine you have a single optical fiber, you can constantly monitor the time alignment between the master and the slave. Okay, since the deep sea is a very stable environment in terms of temperature, nothing happens except in the first layers of the sea, where the temperature effect is can change the propagation time of the light. But this is under control because it happens all together on all the fibers and can be monitored.
Thanks, Giorgio. I think that with this White Rabbit, which is used also in other contexts, in other experimental cases, we conclude the session and we thank you again.
I'm really sorry for being really not, first of all, not present, and then a bit tired after many nights following the detector. Thank you very much for your invitation. And you have questions and whatever, please feel free to ask me. I will be more responsive after a bit of sleep. Thank you very much.
Take some rest and good luck with the installation of the detector.
Thank you very much.
Bye.
Ciao. Bye. Thank you very much.
So we will go to the coffee break, of course, up to 5 p.m., I would say. So we reconvene here at, yes, 5 p.m. for the statistics and so on.